The B-21 Raider can slip past radar, cross oceans, and strike without warning. None of that happens without its engine. The most secret part of the plane, built to be efficient and almost impossible to track, this power plant is rewriting the rules of stealth. When the Air Force started planning the B-21 Raider, the mission was clear. Build a bomber that could fly anywhere in the world, carry both conventional and nuclear bombs, and do it all while staying almost invisible to radar. The aging B-1s and B-2s had served their time, but new threats demanded something smarter, stealthier, and longer-ranged. That's where the Long-Range Strike Bomber program came in, and with it, the B-21 was born. Northrop Grumman designed the sleek radar-evading airframe, but the real make-or-break challenge was the engine. The B-21 runs on two next-generation turbofans, derived from the PW1000G family, designed to combine power, fuel efficiency, and silence, carrying the bomber thousands of miles while masking its heat and noise signature. And it had to be rugged enough to survive combat deployments around the world. Design work kicked off around 2015. Engineers spent years tweaking every detail, from turbine blades to coatings, to make sure the engine met impossible requirements. Then came November 10, 2023. The first B-21 lifted off from Palmdale, California, and landed at Edwards Air Force Base, proof that the design wasn't just theory. And by September 11, 2025, a second Raider had joined the skies, showing this engine isn't just working once. It's repeatable, reliable, and here to stay. Alright, now let's talk about the engine itself, the heart of the B-21 Raider. Remember, the official details are classified, but aviation experts point to a next-generation turbofan derived from Pratt & Whitney's geared turbofan family that powers planes like the Airbus A320neo. For the B-21, engineers adapted it into what's known as the PW9000, with analysts estimating a 4-to-1 bypass ratio. In other words, 4 times more air slips around the core than through it, enough to stretch range and hush the exhaust, without the giant fan that would light up enemy radar. The Raider runs on 2 of these engines, each believed to produce around 17,000 pounds of thrust. Together, they give the bomber the legs to cross oceans without constant refueling. But it's not just about raw power. These engines are built to match the bomber's mission. Sustained high subsonic speeds, efficient long-range flight, and near-silent operation to stay undetected in hostile airspace. And the engine is modular, meaning key components can be swapped out individually, keeping the aircraft in service with minimal downtime. That modularity is what makes the Raider not just powerful, but sustainable in real combat operations. This isn't just propulsion. It's a stealthy, long-range powerhouse, the beating heart that keeps the B-21 flying unseen, fast, and ready for anything. So we know what powers the B-21. Now the bigger question, what makes an engine like that possible? It all comes down to the stuff it's built from. Pick the wrong material and the whole system fails. First up, titanium. It's strong, light, and heat-resistant. That's why you'll find it in the fan blades and compressor stages, the parts that spin like crazy at the front of the engine. Sometimes engineers blend it with advanced composites to save weight without losing strength. Deeper inside, the conditions get brutal. Turbine blades face temperatures hotter than molten lava. That's where nickel-based superalloys rule, exotic metals engineered to hold their strength while glowing red-hot. On top of that, ceramic thermal barrier coatings act like heat armor, protecting metal from extreme temperatures and erosion. Finally, stealth isn't just about shape. Even the exhaust and casing use special alloys and design tricks to reduce infrared signatures and damp mechanical noise. Tiny design choices, a cooled cavity here, a layered shield there, add up to a much harder to detect engine. Put it all together and every piece of metal in this engine has one mission: keep the bomber alive, efficient, and invisible. But how do you actually turn titanium, nickel alloys, and ceramics into a machine that can survive combat? Time to go inside the factory. Let's start with the turbine blades, the engine's hottest, most stressed parts. At full power, exhaust gases can top 1,500 degrees Celsius, hotter than lava. These blades aren't simply cut from stock metal. They're grown through a process called single crystal casting. Molten superalloy is poured into ceramic molds that guide the crystal structure as it solidifies, creating blades with incredible strength to survive heat and stress that would destroy ordinary metals. Up front, the compressor's blades and casings begin life as forged titanium. After forging, they're milled on CNC machines to exact tolerances. We're talking down to fractions of a millimeter because even tiny airflow errors can cause stalls or efficiency losses. For the Raider's stealth needs, even the smaller parts get special attention. Engineers use additive manufacturing, 3D printing, to build lightweight fuel injectors and complex ducts with internal channels that would be impossible to make with traditional machining. Coatings complete the story. Ceramic thermal barrier layers protect hot sections, while radar-absorbing treatments and special surface finishes reduce infrared and radar signatures. Each component then goes through ruthless quality control, microscopes, laser scans, and stress tests, and only the perfect parts move on to the assembly floor. Next up, how those perfect parts are assembled, balanced, and tested before a single engine ever leaves the factory. The B21's turbofan engines aren't built in one go. They start as modules, each crafted and tested on its own. Major sections come first: the fan module, the low and high pressure compressors, the combustor, the turbine stages, and the shafts that tie them together. At the fan station, those wide titanium blades are fitted to the hub and then painstakingly balanced. Even the tiniest wobble could cause vibration, noise, or efficiency loss, all deadly to stealth. A few steps away, the compressor modules are stacked together like spinning discs, each one squeezing the incoming air tighter and tighter as it moves toward the core. Then comes the combustor, lined with special heat shields to survive temperatures over 1,000 degrees Celsius. At the back, the turbine module takes shape, designed to capture that furnace blast and spin it into usable power. Each module heads to a bench testing station. Rotors are spun at high speed to check balance. Compressors are pressurized to detect leaks. Combustors are fired to prove they can handle extreme heat. Turbine blades are checked for cooling flow. Nothing moves forward until it passes. Next comes the final assembly, where everything comes together. Shafts are lined up, bolts are tightened to precise settings, and sensors, wires, and fuel lines are connected. Piece by piece, the modules become a complete engine, ready for the ultimate trials that will follow. Once an engine is assembled, it doesn't go straight into a bomber. First, it has to survive a brutal series of trials that push it to the absolute limit. Inside giant test cells, the engine is bolted down and brought to life. At idle, engineers listen for a clean, vibration-free spin. Then the throttle is pushed forward, airflow builds, combustion lights, and the unit is driven up to maximum rated power, the kind of stress it might see on a mission. Sensors watch every metric: temperatures, pressures, fuel flow, and blade vibration. The real challenge is heat. During hot soak runs, the engine is run red hot to prove the superalloys and ceramic thermal barriers can survive sustained furnace-like conditions. At the same time, vibration monitors check that spinning shafts remain balanced, even at thousands of revolutions per minute. Engines also go through endurance trials, simulating long missions. They're cycled through rapid throttle changes, extreme crosswinds, and sudden shutdowns to ensure nothing cracks or warps. Only after passing every trial does an engine earn its stamp of approval. Fitted onto the B21, it turns a collection of perfect parts into a long-range, hard-to-detect weapon, ready to fly, strike, and disappear. And that's how the engine behind the B21 Raider is built. From exotic alloys to brutal test trials, every step designed to keep America's newest bomber invisible and unstoppable. So, what do you think? Is the B-21's engine the future of stealth aviation, or just the start of something bigger? Drop your thoughts in the comments below. The F-35 is not just another fighter jet. It's a multifaceted beast that combines stealth and design. The strongest fighter jet in America's arsenal started off as a bold idea. One jet that could replace many others, fight in the air, and even hover like a helicopter. So how was the F-35 designed to dominate the skies? Let's break it down. In the 1990s, America faced the problem of its aging fleet. The F-16 Fighting Falcon was fast but not stealthy. The F/A-18 Hornet could fight from carriers but lacked range. The AV-8B Harrier could hover but was unreliable. And the A-10 Warthog was great at close air support but too slow for modern air combat. The Pentagon wanted one jet that could do it all. Thus, the Joint Strike Fighter program was born. The result would be 3 versions of the F-35. F-35A, conventional takeoff for the Air Force. F-35B, short takeoff and vertical landing for the Marines. F-35C, carrier variant with larger wings and reinforced landing gear for the Navy. The challenge wasn't just making a new fighter, it was making a single airframe adaptable to 3 different missions, which was something no one had done before. And at the heart of that vision was one critical component. At the core is the Pratt & Whitney F135 engine, the most powerful fighter jet engine in service today. It produces 43,000 pounds of thrust, nearly double what powers an F-16. The F135 is a low bypass turbofan with afterburner. First, a 3-stage fan pulls in about 400 pounds of air per second, roughly 180 kilograms per second. Next, a 6-stage compressor packs that air to about 30 times normal atmospheric pressure. Fuel is added and burned in the combustor at around 2,000 degrees Celsius. The hot, expanding gas drives the turbines at about 10,000 revolutions per minute, and what's left is accelerated out the nozzle to make thrust. Hit the afterburner, and raw fuel is sprayed directly into the exhaust, igniting in a secondary flame that pushes the F-35 to Mach 1.6. That's not as fast as the F-22 Raptor's Mach 2.25, but the F-35 trades top speed for stealth and versatility. For the F-35B, the engine connects to a lift fan, which is a vertical fan behind the cockpit, powered by a shaft from the engine. It produces 20,000 pounds of thrust downward. At the same time, the main nozzle swivels 90 degrees and small roll ducts balance the jet. Unlike the Harrier, which blasted hot exhaust straight down, the lift fan uses cool air, reducing heat damage to decks and improving stability. Now here's a question for you. How much vertical lift can the lift fan system generate in total? Drop your guesses in the comments and we'll answer this one in the outro. What good is power if you can be seen? That's where stealth engineering comes in. The F-35's shape is designed to scatter radar waves. Its fuselage blends smoothly into the wings with no sharp right angles to reflect radar. It has canted tail fins, the inlets are S-shaped to hide the engine face, and the exhaust nozzle is flattened to reduce radar and heat signatures. The entire jet is coated in radar-absorbing materials. These layers soak up or scatter radar energy. Even the canopy is coated with a thin layer of gold, bouncing radar while letting the pilot see clearly. Weapons are stored internally in bays. Carrying weapons on wings creates radar reflections. So, in stealth mode, the F-35 carries 4 missiles or bombs hidden inside. In beast mode, it can carry 22,000 pounds of weapons externally, but at the cost of stealth. These stealth decisions make the F-35 nearly invisible to radar. In combat exercises, F-35s have scored kill ratios as high as 20-1 against older jets. The F-35 had to be light, tough, and heat-resistant. A near-impossible combination. Engineers solved it with advanced materials. 35% of the jet is titanium, forming its backbone and tolerating high heat and stress. 42% is carbon fiber composite, which is lightweight yet incredibly strong. The rest is aluminum and other alloys. Thermal coatings reduce infrared emissions. Even the paint is engineered to resist heat buildup while remaining stealthy. The airframe was also designed for maintainability. Unlike the F-22, whose stealth coating requires long repairs, the F-35's composite skins are easier to replace and maintain. The result is a jet strong enough to withstand carrier landings but light enough to maneuver and stealthy enough to hide. If the F-135 is the jet's heart, the sensors are its brain. The ANAPG-81 Advanced ASA radar can track dozens of targets simultaneously and jam enemy radars. It can even map terrain with incredible precision. The distributed aperture system uses 6 infrared cameras around the jet to give the pilot complete 360-degree coverage. With the F-35 helmet, the pilot can see through the jet, viewing infrared video as if the jet were transparent. The electro-optical targeting system adds laser targeting and infrared search, and is built seamlessly into the nose. All this data is fused by onboard computers and projected into the pilot's helmet display. There's no need to look at multiple gauges. Everything like the radar tracks or threat warnings is presented as a single picture. Older pilots say it's like moving from black and white television to high-definition streaming. The F-35's internal bays hold 2 AIM-120AM RAM missiles and 2 2,000-pound JDAM bombs in stealth mode. Smaller diameter bombs allow even more capacity. Externally, pylons can carry sidewinders, JSON cruise missiles, and heavy ordnance. The F-35A includes an internal 25mm GAU-22 cannon, firing 3,300 rounds per minute, while the B and C versions use an external pod. This flexibility allows the jet to shift roles instantly. Stealth assassin one day, bomb-laden strike aircraft the next. But no weapon matters without the ability to control the aircraft itself. The F-35 is inherently unstable by design. This instability gives agility, but it requires a fly-by-wire system where computers make constant micro-adjustments to keep it smooth. The jet's software runs millions of lines of code, which is more than any commercial aircraft. It integrates flight controls, radar, sensors, and weapons into one system. For the F-35B, hovering is computer-assisted. The pilot doesn't need to manually balance thrust. With one button, the jet hovers. The system automatically adjusts lift fan, nozzle, and ducts. This engineering choice of using digital control instead of manual complexity made vertical flight practical for everyday pilots, not just specialists. But even the most advanced code needs to be proven in the real world. The F-35 underwent 8,000 flight tests before full production. The Arctic trials proved the engine could restart at -40°C. The desert trials showed it could fly through sandstorms in 50°C heat. They also conducted hover trials, which demonstrated that F-35Bs could transition from hovering to supersonic flight in under 8 seconds. In combat, Israeli F-35s have struck Syrian targets undetected. USA's F-35s have flown missions in Iraq and Afghanistan, integrating seamlessly with older jets. Critics argue about cost and maintenance, but its battlefield performance proves the engineering works. But to really understand what makes the F-35 different, you have to look at where the pilots sit. Step inside the cockpit and you'll notice something unusual. There's no traditional head-up display. For decades, fighter pilots relied on a HUD to project speed, altitude, and even targeting onto the canopy glass. The F-35 throws that out entirely. In its place is the helmet-mounted display system, a $400,000 piece of engineering that turns the pilot's visor into a full panoramic screen. Every piece of information is projected directly onto the helmet. Using the distributed aperture system, the pilot can literally see through the jet, with infrared cameras projecting live video beneath their feet. Wherever the pilot looks, sensors and weapons follow, allowing them to lock and fire simply by aiming their eyes. Each helmet is custom molded to the pilot's head, ensuring the displays are perfectly aligned. This philosophy reduces workload and increases awareness. Instead of juggling dials and scopes, the pilot sees one fused picture of the battlefield. For the F-35, information itself is the ultimate weapon. The F-35 story begins with the X-35 prototype built by Lockheed Martin. The X-32 had a large, ungainly intake and struggled with vertical flight. The X-35, in contrast, successfully demonstrated short takeoff, supersonic dash, and vertical landing in a single flight, and it was the first jet ever to do so. That win secured the Joint Strike Fighter contract. Lockheed Martin partnered with Northrop Grumman and BAE Systems, while Pratt & Whitney built the F-135 engine. The program ballooned to over $1.5 trillion projected lifetime cost due to delays. Yet despite criticism, the F-35 is now the most numerous fifth-generation fighter with over 1,000 delivered. Now let's answer that question from earlier. The lift fan system makes 40,000 pounds of vertical lift, which is enough to raise the 30-ton jet off the ground. The F-35 Lightning II proves that it is more than a fighter jet. It's the most ambitious engineering project in aviation history. If you enjoyed this breakdown, like and subscribe for more deep dives into the world's most powerful machines.